All right, well, good afternoon, everybody. My name is JeanHeyd Meneide, otherwise known as the PhD. I am a student who spends a lot of time working with, making various different libraries, whether it's Bits or Lua or wherever else. And now I've kind of turned my attention towards Unicode. And so what this talk is going to be about is the plan that Study Group 16, the Unicode arm of C++, is trying to come up with to fix a lot of the problems that Unicode and text encoding and handling have in C++. So, obviously it's 2019 right now, and the story for kind of Unicode and C++ is that it's really bad. We had things like wstring convert in the standard a short while ago, but we kind of need to pull that out because it was really bad at performance and it was kind of poorly implemented, mostly because of things like std locale. The general code convert and the facets on streams and everything else are kind of really bad to use. They have virtual interfaces. It's hard to have data polymorphism or data type extension. And more or less, it's been very, very painful trying to get any sort of Unicode support into the standard or into any of our current interfaces. And so what makes text conversion hard, right? So obviously there's streams, there's facets, there's wstring convert need to be pulled out of the standard, but what other things really make text and encoding and all of these things difficult in C++? So one of the biggest problems is that locale and encoding are sort of conflated together. So every time you have a std locale object, that locale object, ships with it the idea of not only an encoding, but a bunch of other things that are related to like internationalization and localization. So for example, if you're using a dot instead of a comma, money punctuation, and all of these things are kind of stored in the locale. But when you do that, right, you tie together this idea that every single internationalization entity also needs its own locale with it, and also needs its own encoding with it. And so when you have that strong coupling between an encoding and a locale, you end up having a situation where every single locale for all the different cultures in the world tend to roll their own encoding, and that's kind of what they did for a very long time. Just a couple examples, right? If you have a file and you have non-ASCII bytes in it, and you save it in Germany and you ship it to Japan, I mean, you might as well just start crying when the bug reports start rolling in. If you use /UTF-8 in an MSVC, which is like the way, right, what you're supposed to do, but you forget to save your file as UTF-8 in your editor, you're going to have a really bad time. And of course, if you just generally just ship code to a platform that you don't completely own, right? The locale is different, and there's tons of bugs, whether it's in video players or VLC or just anything, where it's very hard to reproduce a bug that's locale dependent because you open up on your machine, nothing about the C APIs, the C++ APIs really tell you that they're using the locale, and so you have all this locale dependent behavior that you just kind of magically assumed work in your beautiful, nice English PC, and then you shipped it over to Turkey, you shipped it over to China, you shipped it over to India. It parsed things differently, it handled numbers differently, and everything went down the toilet. So this is like a really, really big problem. The other problem is what is the encoding? So it's tied to locale, but it's even if you want to try and figure out, it's impossible because for things like car, for the narrow encoding, it's whatever the system feels like at the moment, right? So you can change it with the lang environment variable. You can use set locale during runtime, and it's not just you use set locale in your program during runtime. Like some library over there in one of your dependencies calls set locale, and it changes it for everything because it changes it for the whole process. The active code page on Windows, the fact that your computer that you opened up and booted up your computer and set it all up in France, and you moved to the U.S. and you're wondering why are a couple things not working quite right. All these things, right? And you would think that wcart, which was supposed to be the solution to this, would be better. And it kind of was, right? So UTF-16 is what Windows and IBM had to kind of settle on for wcart, and most other systems use UTF-32, except that IBM platforms, if they're compiled for 64-bit, choose UTF-32 and then use UTF-16 otherwise, except if you're on a Chinese locale and they pick some other flavor of Big Five or one of the GBK encodings. So even the thing that was supposed to solve the problem didn't solve the problem, and so we're still kind of back in the problem of like what when you have a literal, when you have a string literal, when you have a wide string literal, what does that mean? What is the encoding? And the answer is whatever your compiler decided and whatever your system decided. So, again, we wanted to have these Unicode literals, right? So we created these Unicode literals for car16t and car32t, which you would think naturally should be UTF-16 and UTF-32. Turns out that's actually not the case. There's these two macros that can tell you whether or not you actually have UTF-16 or UTF-32. The good news is that we've surveyed almost 100 different compilers in a bunch of different places, and it turns out that everybody thankfully did the same thing and picked UTF-16 for car16t and UTF-32 for car32t. So what happened is that Robot Martino Fernandez, he submitted a paper, P1041, that basically said, listen, let's just be explicit in the standard. Let's not have this waffle wording. Let's not, try to describe surrogate pairs without talking about real surrogate pairs that come from UTF-16 or any of that, right? Let's just make them UTF-16 and UTF-32. And so we did that. And so thanks, because that really helps, right? And the other problem is, right, maybe we think about streams, right, IO streams. And I talked a little bit about that. But the problem with IO streams is that we've actually sort of boxed ourselves into a situation where it's actually fundamentally impossible by the standard to support encodings that go beyond 1 byte or 1 unit at a time. And this is what kind of colloquially referred to as the one-to-one rule, the one-to-one restriction. And what it basically says that if you were to convert multiple, say you have a UTF-8 literal, right? And you picked the wine glass because that's what you want to do. And you were serializing it to a CS+ stream. A wine glass is 4 bytes, right? And so the idea behind this rule is that if you were to serialize all 4 bytes and it says that, and it will return yes, everything went okay, right? It returned the error okay from the codec conversion functions. What happens is that the implementation is allowed to truncate that to just 1 bit, serialize only that 1 bit, and then return okay, right? So in factuality, it's nearly impossible to support anything that has to do with multi-byte encodings, with multi-unit encodings. Just the standard fundamentally restricts this. Now, important to note, it only restricts it in the case of basic file buff. The problem is that basic file buff can represent a lot of things, right? How many things can a file descriptor on a Linux machine represent, right? So it affects your console, it affects your files, it affects maybe even the network. It's basically invasive to the entire stack. And so there's really no way to fix the CS+ streams, right? Even if we were to move the restriction, right, there are people who have a buffer of size 1 sitting at the other end of this thing, expecting to only serialize 1 bit in it for it to return okay, right? And if we break that invariant, those people are broken, right? And they're not broken in like a loud, noisy way, right? This is a virtual interface, right? This would be a requirement change that we would change silently behind their back and say updating the standard version. They would update their version and suddenly, we start overrunning their buffers, right? And that's a serious security vulnerability, right? There's no way that we can actually fix a lot of this stuff in C++. Also, one of the biggest problems is that a lot of IO streams and code convert and facets are virtual, right? And you may think, well, we could just add another virtual function. And even if the implementers do great magic to make it so that it takes the virtual function and puts it at the end of the V table, so that when you start calling things, it doesn't mess up the V table of old things, somebody outside the standard may have actually derived from one of the facets or streams or locale objects, and they have their own virtual table that sits on top of the one that implementers shipped. So you may guarantee that you put something at the end and your rest of your V table is fine, but you just moved everything down for another person who derived from your type, and you basically just ruined their day because then all of a sudden virtual stars got flying all over the place. They have no idea what's going on. They're just like, I just upgraded my compiler and ran some stuff, and all of a sudden I'm getting all these crazy spurious failures, right? And so again, we're kind of in a virtual function hell. We don't have any non-virtual functions that are well specified. And so basically, we're pretty much hosed in the current landscape. And so, C really isn't no better. It's not really much better. We have, singular code unit conversion functions, but the problem with those is that a lot of them assume that one input is kind of equivalent to one output, or one output is kind of equivalent to one input. And so anything that's pretty much not UTF-32 like for WCAR-T like I was talking about before is basically wrong. The R in some of these functions mean that they are restartable functions, and what that means is that they have an extra state parameter where they can store some extra stuff. But the problem with that is that it's still not specified how you use that state and return. There's a defect report actually out for the C. You wouldn't think that the C committee is still receiving papers and alive, but it's actually still alive and they're actually still going. And they actually recently opened a work item for C2X to come out soon. But the problem with a lot of these functions is that they have fixed interfaces and it's impossible to properly convert a stream of multiple bytes, right? Multi-byte encodings or multi-unit encodings. And of course, one of the things that they don't have is that even for multi-code unit, they don't have it for any of the Unicode functions. And right, even if we have the single things, right, we could just loop, right? How bad could it be, right? So this is a bunch of code that actually comes from CP reference showing you how you loop, how you use MBR2C32. And what that means is multi-byte string restartable to a Unicode a car32 string or car32 character. And when you do this, right, you're able to kind of loop through all the characters and convert everything, right? And it's pointers, it has error codes, there's no exceptions, it's pretty easy, right? The problem with this is that it's slow. It's terribly slow. Looping and doing code conversions one at a time is not a good idea for literally anyone, right? But this is the only this code right here that you see is the only way you can kind of do this today in the standard to go from a literal of a regular literal that you put in quotation marks to a car32T literal. And so again, it's terribly slow. There's no SIMD possibilities, right? Because the whole point is that the function that's called, that's usually compiled into like libc or glibc or the VC++ C library, and so that's usually hidden behind a DLL or a compiler barrier, right? So there's no way for the compiler to see what's going on inside of that and just optimize the whole loop, right, and get you all of the SIMD or vectorization possibilities. And also the restartable versions have a little bit of code overhead, and the only versions we have for the car16, car32T conversions are restartable. So we're a little bit hosed there. Small bit of a digression. Anyone know what this function is supposed to do? Right, just call it out, right? It's MV2 Wide Character, right? So anyone have like an idea, like how this is supposed to work, right? Anyone call out like nobody. Oh, Peter has a.
You give the multiply string and then it outputs wide characters for some value of number.
Right. So Peter's response was that you put in a narrow string and you get out a wide string of for some amount of numbers, right? And actually, this function is a bit of a lie. You see the WCART pointer, pointer to wide characters, right? And this looks like something that would be able to handle multiple code units, right? So, for example, you have UTF-16 on Windows, right? So if I had a regular string literal in, UTF-8, because we're going to pretend that Windows supports UTF-8, it actually does, but not for everybody, but it does. We put a UTF-8 literal for MBS, right? And we give it the size, right? And then we have an output buffer, right? We have like a large output buffer for pointer to wide characters to write to. The problem here is that this isn't actually like an output wide string. You're only supposed to output one character at a time because that's the contract that this function has, right? But because it's a pointer, it looks like it's an output like buffer thing, right? So please, pretty please, stop using pointers to represent optional values. Obviously, this is C, so we can't get that, right? So we can't have that nice thing, but there are C++ versions of this that still kind of do the same thing, that still use a pointer to a car type to have an output buffer without any kind of other sizing information. And the conventions are nice. The convention of always having a pointer to a character type being a string or a variable amount of things is nice until it's actually wrong, right? So just, don't use pointers for optional values in C++ interfaces, right? I spent actually a long time looking at this because I thought that this supported like multiple UTF-16 code units, right? So having the surrogate pair and then the other part that tells you, what they have a wine glass, right? Or a snowman or man in levitating in business suit, right? And then I used it and I only got out like half-broken surrogate pairs, and I sent an email to Billy New. I was like, I'm sorry, isn't Windows UTF-16? He's like, no, it's UCS2. It doesn't support more than 16 bits. And he gave me a kind of quick rundown about the one-to-one rule and this stuff like this. But of course, when you look at this API, it's impossible to tell that because it's a pointer, right? It's a pointer. Like that's the convention, right? You assume that it's a multiple thing, that it can handle multiple things, but it can't. And so that's kind of unfortunate. So, but that's just kind of like a quick mini rant about optional and stuff like that. But this is kind of the full landscape of all the stuff we're missing. There really only are two check marks on there. And then we have these R's in the table that represent that there's a restartable version, but not a non-restartable version. But basically, like all of this functionality is missing from the C standard. So there really is no good way to convert from a regular string literal to any one of the Unicode ones or backwards, or any of the wide ones to the Unicode literals or back. And it's kind of very much a sad state. There's also all of these APIs use null terminated strings. Even the S ones that are supposed to take an actual string parameter take null terminated strings. And so if you have an embedded null in your Unicode, well, I hope you're ready to like check and loop and do all this stuff, which is again more of an impediment to performance once again. So I might be proposing a paper to WG14 to fix this, but it is a lot, and the WG14 C committee has this rule that you're supposed to have 2 implementations. One person implemented this already in the small device C compiler, but they need one more person from like Musil or glibc or whatever else. So I'm slowly gearing up to step into the world of glibc and say goodbye to all the nice abstractions in C++ and write SIMD and C, and oh man, that's going to be great. But I've managed to convince you, right? So fine. C++ are terrible. But you say, but we have third-party libraries, maybe, right? Like that's what C++ is all about, right? If the standard doesn't give it to you, right, you can just make your own library, right? And it's gonna be great. It's gonna be amazing. It's gonna be. No, it's not great. It's not great at all. But to be serious, right? There is ICU. But it's a dumpster fire. My apologies to the ICU implementers, right? You did a great job when you made a nice Java API, but then you ported it to C and didn't go quite well. And then you like wrapped the C that you ported from Java into C++, and that didn't quite go so well. It's horrible. I tried to use it actually because I wanted to like compare like my API and other people's APIs to it, and it's not fun. Most people actually don't even use ICU. They either use uconv or iconv, which is like the POSIX wrappers around those things. So they really just have one function call, and they don't have to worry about any of the other stuff. But man, ICU is hot, flaming garbage. The good news is the good news is that like it's hand optimized, right? It's probably one of the most fully featured, fastest implementations, right? It has all the algorithms, it has all the data you want, right? It has everything, but it's just the API is really bad, right? And so when I started on this, right, I was like, why didn't everybody just use ICU, right? If that would solve all our internationalization and localization and encoding problems, right? And then I actually used it, and I was like, so now I understand, right? And there's a bunch of several ad hoc libraries out there, like the UTF-8 CPP library and a bunch of others, but they're very hyper-focused. They don't include a lot of the Unicode algorithms. Some do, some don't. It's basically hit or miss, and you just kind of stumble upon, or you just end up implementing it yourself in a fit of rage one day. But there are some good libraries that are more current. So Boost.txt is something that Zach Lane, the first guy there with the handsome beard, he made Boost.txt. And what he does is he handles encode and decode and a lot of the higher level algorithms, right? And he did a from scratch like clean room implementation of it. And so it includes bidirectional algorithms, segmentation, collation, a bunch of stuff, right? I don't think they include regex because that's really hard, but if you want to do that, just talk to Hanna Kusakova. There's also 2 other libraries. There's liboganek and TextView. Liboganek is a library that came from Robot, the guy who wrote the other paper to fix the car literals in C++. And another library called TextView, written by Tom Honerman, the last person there, who is actually the chair of Study Group 16, SG16, which is the Unicode arm of C++. And so the liboganek handles a lot more than TextView does. TextView kind of got all the way to like encoding and then kind of stopped there because he has a real job and a wife and kids, and you can't just do this forever. And Robot is sort of in the same boat in that he got encoding, decoding, and a lot more features. But it kind of, but he's ran out of time to develop it, right? So kind of talking about some of the ups and downs here. Boost.txt covers, it covers the widest variety of Unicode algorithms outside of ICU that I've seen so far. It also uses STL constants, right? So it has ranges and iterators and the same kind of container stuff. The only downside to boost.txt, literally the only downside to boost.txt in Zach Lane's work is that he's opinionated. He has very strong opinions. If you come to an SG16 meeting, you'll know what I'm talking about. But he decided for everybody, right, who uses library, right, that UTF-8 is the one and true God, which is kind of true, but also he fundamentally chose the normalization form C, FCC normalization, and those two. While it's good for him to fix those things and kind of decide for everybody that that's what they want. There's a number of different reasons why you would want to pick other normalization forms or even other storage schemes. And so that kind of serves as like a downside as far as like having it consume a lot of the current problems that we have today, right? Because other people have different kinds of encoding requirements. Other people especially want to use like normalization form D for internal processing and other things like that. And so because he's fixed the internal representation normalization forms, it's kind of like hamstringed him or hamstringed his library. libogenek, right? I'm not going to talk about TextView because libogenek basically does all of what TextView does, but like better and further. It provides many of the Unicode algorithms, including normalization. It has a concept-driven design with iterators, and it has actually pretty good speed, but it's not really recently maintained. It was started, I think, back in like 2012, and he did a lot of work on it and got really far. But he got a job, life, wife, etc. And then there's a couple of issues with like the iterator approach that he used, and I'm actually going to talk a little bit about how libogenek did some of this. So he had his approach was entirely range-based and entirely iterator-based. So he was actually able to do all the Unicode algorithms, but like keep with STL concepts, right? So you could take his iterators and like pass them to STL algorithms, and it would work, right? The only problem with his setup is that when you start stacking a grapheme iterator on a normalization iterator on a decode iterator to do your algorithm, you end up having to copy and store a lot of iterators on iterators and a lot of state. And what that ended up doing is that you ended up with these really chunky iterators, like these really beefy iterators, right? 256-byte iterators, right? And you're trying to pass these things by value on the stack. That's real painful. And a lot of these iterators need to both begin and end inside the decode iterator so that it would know when to stop or when to throw an error and other things like that. And of course, because in C++17 and below, every single iterator pair had to be exactly the same type, you ended up having two 56-byte iterators twice, where one of them really just had like booleans and a couple of flags to say I'm the end iterator, right? And the other one was just had all the extra information, but both of them were the same type, so you had these two really chunky iterators. And of course, you stack them like this, where you do, you wrap three iterators at a time with additional information, and you end up with these really, really big iterators. And so the fix for this is actually stood ranges. So stood ranges lets you have a different end type than a begin type. It lets you have a sentinel type. And what that means is that the sentinel type can basically just be a completely empty class or structure, and you can still compare it against the first one and use it to basically trim down all the state. So what happened is you usually have these big, chunky, big boy iterators, and now they're nice, small, crescent moon, sleek iterators, right? So separate types, begin and end, and so you only have all of the information in the decode iterator, or all the information on the one half of the equation, right? And you're able to optimize that and make it small and tiny, and it's great. There's also other APIs. So this man here is Henrysaponin. He does a lot of work in Helsinki. He represented Firefox actually for a long time to the web standards body, and he did a lot of work on working on like basically the conversion routines that are in Firefox, right? And so talking about the Firefox and Chrome database code bases, right? The routines they wrote are extremely fast, right? They need to convert a lot of text, right? They're handling web pages. They need to basically like take stuff in, process it really fastly, dump it out, right? And they need to also have kind of like consistency between them, right? So the way they handle errors, etc. So it's very highly optimized implementations. The problem is it's still kind of pointer-based, right? Like the C interfaces. So it becomes a little bit problematic if you want to use it with exotic storage. So if you wanted to say use a std_dec, well, it's a little bit difficult. If you want to use, say, a rope, it's a little bit difficult, right? And again, one of the problems is that the Chrome stuff and the Firefox stuff are generally code-based specific, except Henry went out of his way to release what's called encoding.rs as like a freely available library, and he has C++ and C bindings. So he made a serious effort to allow other people to use his code, right? And that's been very, very, very helpful. All right, but now we've kind of talked about the landscape. And so now we're kind of going to spend the later half of this talk kind of talking about the things that we want to do, right, with text, the way that we want text to show up in the standard. So here's one of the goals, right? We want to be able to have a stood text, this nice like U8 text type, right? We want to be able to hand it a literal and tell it to transcode from this like narrow string multi-byte encoding type to UTF-8 and just have that work right out of the box. Right, and we also want to be able to print it out to stood out and whatever else, right? You obviously need a capable console. Microsoft Terminal is actually capable of UTF-8 and stuff like that, so this might work in a future coming to you actually pretty soon. The way this works is we kind of need a container adapter. And so the fundamental of this is that we have something that takes an encoding, a normalization form, and then a container upon which we build, which we write these abstractions around. And so it follows the same coding conventions that's in the standard for other containers like basic strings. We have basic text, and it's all templated to hell. Similarly, we also want a text view type so that you can take a bit of storage that you don't actually own, but still view it as like a sequence of code points, right? Which is incredibly useful. And so this is the other type, basic text view. And obviously, you don't want to type out basic text every time or basic text view, so we have some convenience aliases here, right? So you have U8 text, U16 text, U32 text, W text with wide execution, the W car, right? Whatever the user sets or whatever the platform sets. And then we have text, which is UTF-8. No, I'm just kidding. It's narrow execution. I would love the pipe dream where we could assume that the default text type is UTF-8, but no. This is the reality check. So text is narrow execution. It's not UTF-8, which comes with its own set of problems. But you might be wondering, why these view adapters, right? Why these things that we build? Why don't we have a stood text container all by itself, right? Without these like adapter things, right? Without having like these things that wrap strings or whatever else. And the problem is that the thing that we want to fix is we want flexibility, right? If STL, if Billy O'Neill, if Jonathan Wakely, if Eric Facelier have to sit down and write yet another container and provide the strong HTTP for yet another thing that is essentially stood vector, we're not really succeeding, right? And plus, there's a bunch of different storage mechanisms that already exist in the world, right? So there's things in the standard already like DEC, but then there's things like LLVM small vector. There's things like in the extensions namespace of GNU, there's a rope type. There's an actual rope type that like, you can use to store text and everything. There's gap buffer implementations. There's ring spans. There's more and more things that you want to have with this, right? And we really can't afford to reinvent this thing or have other people reinvent this thing every time they need a new string type, right? Like, obviously, I mean, it'd make the game devs happy because they'd have something to re-implement every single day. But, we want to keep this simple. We want to keep this easy, right? And even then, ICU makes sort of the same mistake in that they have their own Unicode string type. And of course, you're not going to cart around their Unicode string type in all your APIs, right? So, again, it's not fun. We don't really want that. And the thing is that we want, the biggest sell here is that nothing changes for the implementers, right? So you have a function, right, in thing.http, and it's do the thing, right? And it takes a stood string, which is totally UTF-8, right? It isn't actually a U8 string, but like your code base and your convention says like, listen, I have car, we've already defined it to be UTF-8, I don't want to do any extra effort, whatever else, right? And so the idea here is that with these container adapters and these view and these range adapters, you can actually have your same interface. Nothing's changed for the user, but internally, you can use U8 text, right? You can move the storage into this U8 text. You can use it. You can do all the stuff you did before, but without having to like manually keep track of code points. And then you could just return the same thing that you always returned, right? And so this means that porting and that having people opt into this interface is a lot easier, right? You don't have to go change your ABI, change all your source code, check if all the things still build. You just do it internally, right? And you still get all the same benefits. There's also some other goals we want to talk about, right? So let's talk a little bit about networking. This is an example from the Beast library. I've obviously trimmed out a lot of stuff because there's a lot of work that goes into maintaining this kind of stuff. But we have, an HTTP request. We have a vector that is the body of bytes that we get back from this HTTP request. And then we have this kind of U8 string, this converted body thing that represents the body that we're going to take that's going to be the converted information. And so, of course, there's the usual beast boilerplate. We have to on-connect, on-resolve, on-read. But what we're really going to want to work on is the on-read function. So we're going to look at that a little bit. Obviously, there's the usual boilerplate, right? You got to check if the error code fails and log a failure and return. That's how you cancel things, whatever. But here's what we've checked the error code. Now we're going to do the interesting part, right? So we have bytes. We have some bytes. We got them out of the response body, and we check the bytes transferred value, right? And we put that in a span, right? So we have a span of bytes, right? Your typical useful stuff. Now, what we do is we have this new kind of interesting type called unbounded view. And what that does is that takes a single iterator and basically acts as this kind of magical output type that you're allowed to kind of dump things into infinitely. We then have this interesting encoding type called encoding scheme, where you give it a normal encoding, but then you can specify additional parameters such as, I want it to be big endian, or I want it to be little endian. And the whole point of this encoding scheme is that you don't actually have to re-implement, right, like UTF-16, but for big endian, UTF-16, but for little endian, UTF-16 for PDP endian. I don't know who has still a PDP machine, but it's possible. And so the idea is that you can go from this UTF-16 that's in big endian to UTF-8, and so you just call std TextTranscode. You give it an input range, an output range, the encoding you're coming from, and the encoding you're going to, and it converts everything, right? Just like that. And so in there, and obviously here we're just going to kind of output the converted body because, we don't have anything else we want to do. And so, but this is kind of, right, all the stuff we're doing here, this is like the dream, right? This is the top level, like text is easy. You don't have to worry about it too much. This is what we're going after. So I want you to keep this dream in mind as we start going a little bit lower into like the layers of like how exactly are you doing this std text stuff? How exactly are you doing this basic text view, these encode views, decode views? What does that mean? What does that look like? So we're gonna start digging a little deeper into the API, right? Into the thing that I've been working on that I'm going to be proposing eventually for C++ standardization. Obviously, at the foundation are these encoding objects, right? And you saw them before, right? You saw UTF-8, UTF-16, UTF-32. You saw ASCII, narrow execution, wide execution. There's a bunch of stuff that are basically encoding objects. And what these objects are is they serve as this foundational building block. And the idea is that these building blocks allow you to have seamless transcoding from one end of an API to another end of the API, or can encode from one encoding to another encoding without having to worry too much about all the inter details. So I'm going to set up a couple examples here where I'm going to use some helper types, right? So we have a span of car8t, we have a span of car16t, a span of u32t. We have this like empty struct type that's going to come in handy later. And we have this like encoding error and enumeration class. We also have some result types that we're going to be using. So the idea is that if we have a decode result, right, well then we have the input, the output, the state that we were working on, and then the error code, right? And it's the same thing for the encode result, just the U32 and U8 span are flipped around for the input and output. We also have a little bit of some error handlers. We're using Vittorio's, we're using Vittorio Romeo's std FunctionRef as a kind of a lightweight, easy to compile reference to a function. And it has a signature that it returns an encode result or decode result after it takes the initial encoding and the result itself. And we'll explain this, but we're just kind of setting up the example. So here is like the full nitty-gritty details of an encoding algorithm with all the necessary members. And so the idea here is that you have an encode function which takes an input, an output, the current state that you have, and an error handler. We also have a decode function which takes a decode result, takes the U32 span, U8 span output, you have the state, and you have an error handler. Then there's all these type defs at the top and some of these other things. And so the idea here is that you can define a code unit, which is the individual pieces of what make up an indivisible unit of information. We have a code point, which is the actual indivisible unit of information after it's been decoded. We have a state type, which basically says, this is the state I need to keep encoding and decoding stuff whenever you call me. And then we have these two special, like mathy sounding, is DecodeInjective, is EncodeInjective. And we're kind of going to go walk through a lot of what this means. Of course, we're going to show you first the thing to scare you a little bit. This is actually what the Gory details in the standard would look like. And this is actually what I've been implementing. And so it's like static constant spur. We take templates everywhere and et cetera, et cetera. But I very much like the span-based, like simple, clean implementation. So we're going to talk about it in terms of this, right? Obviously, all this Gory stuff is just like to handle like arbitrary iterators that you hand me from like an iStream iterator, so we can handle like forward and like only input-only iterators and whatever. But that's, again, all the gory details, and we're going to kind of talk about this in the higher level terms, right? So code unit, right? Like I said, this is the thing that gets converted to individual code points. And so there's various different kinds. There are various number of code units that you can have. So for example, for UTF-8, as we saw on the last slide, there's a max code units of 4 and a max code points of 1s, right? So the code units we can have from UTF-8 are from 1 to 4, right? Or 1 to 4 bytes, right? UTF-16 is 1 to 2 code units, but each code unit is 16 bits, so it's 2 to 4 bytes. Then you have UTF-32, which is 1 code unit, but it's 4 bytes for each code unit that you have. There's ASCII, which is 1 code unit to 1 byte, which is going to present an interesting case for our framework here. Again, we also have code points, which is, again, this is an indivisible unit of unambiguous bit of information, right? And so the whole point is that this can introduce, this represents basically everything that the encoding can vomit out, right? The point of Unicode, again, is that it can kind of encapsulate everything. So a single CAR32T, a single UTF-32 code point should be enough for everybody. There's also, again, like I said, some interesting problems with things like ASCII that we're going to talk about. But again, it's generally the code point type def is usually just CAR32T. The state is just a structure that contains all the things necessary to do stateful transformations. So in things like ISO 2022 JP, there are these like shift states or modes that can be encoded into the stream. And once you see those, you have to change the way that you interpret the following stuff, right? And so these are stateful encodings that require this kind of state parameter you to fill it out and do extra stuff with it, right? But thankfully, the Unicode encodings, or the three ones that we care about, UTF-8, 16, 32, are all stateless. So that's why we use an empty struct, just state equals empty struct, right? And that's totally fine. All right, and so now let's talk about the encode and decode functions, right? So these are basically two functions that take an input range, an output range, the current state, and an error handler, right? And it computes exactly one, and only one, indivisible unit of information, right? So you go from multiple code units to one code point, or one code point to multiple code units, right? And you can modify the state and do one of the above, or you output an error, right? You return an error code, or you throw an error, or you replace the text in the stream with a replacement character. The default that we're actually going to have for the library is the replacement character, because there is so much malformed text in the world that if you were to actually have a throw error handler by default, you'd actually DDoS like half of the world. And that's probably not a good thing to do. So replacement text error handler is the one that gets used by default. And now you may be wondering about this thing called an output range, right? Because you have output iterators, right? So like the stream iterators, etc. But the idea behind an output iterator is that you can basically have sized outputs, right? So if you've ever worked with C++ for a while and you've ever used the algorithms like copy-n or copy, you'd notice that they take only 3 pieces, right? The iterator, or the iterator and the size, and then only a single iterator as the output iterator, right? And that's very easy to make unsafe, right? I can easily run over my output buffer, right? And just smash my stack, destroy things, create a security vulnerability, whatever else, right? The thing about output ranges is that they contain both the beginning and the end of the output, right? So I can have a span of this output here, and that allows me to say, listen, you only can output 16 characters the size of my string, and then you've got to stop, right? And then I get an error back that says, and then in the result type I get an error code that says, insufficient output, right? Insufficient output size. Of course, there are those people, right, who will say, listen, I checked my sizes, I checked my buffers, I don't need your safety, right? And so this is one way to get more speed out of it, right? More, they don't need your safety, right? So this is something called, the unbounded view. And the unbounded view takes a single iterator and has this like unreachable sentinelity. So it's basically like it counts from 0 to the end of time, right? And so you can keep using that iterator, keep incrementing, and it'll always compare, and every time you compare it to the end, it says, yep, there's still more space, right? And you can totally overrun your buffer, but this is for the people who are like, yes, I've checked everything, it's totally safe, it's fine. For the people who are extra dangerous, right? So you want to live super dangerously, right? So you can not only use the unbounded view and just pass the pointer and say, keep writing to the end of time, you can also pass an assume valid handler, right? So there's a cost to calling the error handler and say, listen, you need to call the error handler, you need to check that things were right, et cetera, right? What if you have some text in the database and you've already totally, made it so that it's UTF-8 all the time, you know this, you've checked it, it's great, right? So in this case, you have to explicitly say assume valid handler, right? And so this is your way of opting into not only maximum speed with an unbounded view, but not only maximum speed with the unbounded view, but to say, listen, even if I have bad code points, just ignore them, right? Everything's fine. Assume valid handler, just keep going. And again, this also makes it very easy in your code bases, right? So rather than looking for every single instance of copy, which happens to take 3 iterators, instead you have a very explicit way of saying, listen, I opted into the undefined behavior. So if my code starts exploding, I know what I need to grep for first to find the problem, right? And this is, again, for safety and all of that stuff. Now let's talk about these kind of mathy things. So is DecodeInjective, is EncodeInjective? And so the whole point of these is to provide additional safety to higher level APIs and even some of the lower level APIs. And we're going to kind of illustrate this with the ASCII encoding and the ASCII problem. So this is a cute little dog emoji. We have it in a UTF-32 literal. The whole point here is that there's no way that ASCII can represent that, right? There's no byte sequence in ASCII that represents the dog emoji, right? It just doesn't exist, right? And so the idea here is that we want to static assert when the encoding or the decoding might not actually fit, what it's trying to do, right? So to give a bit of an example, here's the top part of the ASCII encoding. So going from ASCII to Unicode is fine, right? You can widen that just fine, right? In fact, that's like if it's going from ASCII to UTF-8, that's a mem copy. If it's from ASCII to UTF-32, you can use like a widen, SIMD, and all that other fun stuff. But the whole point here is that decoding is perfectly fine, right? That's a valid thing you can do. But going from Unicode to ASCII, right? Going from the dog emoji, right, to some ASCII characters is not fine, right? It doesn't work, right? So the way you opt into this is by saying, is EncodeInjective false type, right? And by defining it as this false type, what it does is it makes sure that if you were to write something like this, if you were to say, listen, encode this dog emoji as ASCII, you get a compiler error, right? And the compiler says this is a lossy conversion. You can't do this, right? It doesn't work, right? And so this is, again, for safety, right? To make sure that people don't accidentally start cutting up and trimming things that they didn't really intend to do. And so as another example, right, if you were to pass the default text handler, right, and you did this, right, you still get a compiler error. But if you were to say, listen, I know what I'm doing, I'm using the ASCII encoding, but I want the replacement handler, right? And so what happens is we'll replace the dog emoji with just a question mark, right? Because that's all the ASCII can handle, right? So you get a question mark out, and code will compile now, but you specifically ask for the fact that, listen, I don't care if I lose information, right? Just replace the text or throw an error or whatever else, right? And that's the way that you do that, right? So you have to be explicit. And so just as a quick overview, these are all the encodings that you want to provide in the standard, right? So we have the ASCII, the narrow, the wide, UTF-8, 1632, but we also have these other types, right? And the reason we have these basic UTF-8 or basic UTF-16 or basic UTF-32 is because there are plenty of code bases out in the world where they don't have the time to port everything from CAR to CAR8T, right? So you should be able to pass CAR to basic UTF-8 and form your own UTF-8 handler that works off CAR. I don't recommend it because CAR can be signed or unsigned on a certain platform. And so if you happen to be doing some Unicode math, right, you can accidentally start truncating or missing or mangling the text. So please don't use CAR. But we live in a world where people already do that, right? And I can't actually get them to completely rewrite their whole code base, right? So this is their way out, right? They got to be explicit about it. They got to, use the basic UTF-8 stuff. Everybody else gets the nice stuff, right? You get the nice CAR8T, CAR60T, CAR32T short names. So that's a full overview of the objects itself, right? So now I want to talk about beyond the objects, right? So we have these low-level encoding objects, and you have these singular encode one, decode one at a time functions, and they're nice and they're pretty, and you can put them together to make interesting things. Sure, but we need some speed, right? I showed you that slide before where we did the loop over the MV2 C32 character thing, right? With the C function, and that was a slow loop, and the performance was terrible, et cetera, et cetera. The performance of this is also terrible, right? But there's more. And so what we have here is a three-speed approach. And the idea is that there's the slowest path, which is the round-trip transcoding. It's very lazy. It does one thing at a time. Very, very nice. Then there's a faster path where you directly transcode. There's no round tripping, but it's still lazy. And then there's the absolute fastest path, which is bulk processing, ear consumption. Give me all the code points at once. I will transport them all the way to the other encoding all at the same time, right? So let's talk about the slowest path, right? So we have this nice little diagram here. Basically, you have an encoded single input, right? You decode that to a Unicode code point. You take that Unicode point and you encode it to the other thing, right? And then you dump out the single output character, right? Or the single output unit of information. And this is good for disparate encodings, right? If I need to go from Shift.js to GB18030, which is the Chinese, which is the Chinese, which is the national Chinese encoding, I can't I can't write like a routine that swiftly does that, right? I need something that like decodes to Unicode and then takes the Unicode and puts it back into the Chinese encoding, right? And so the idea is that we always round trip to Unicode because always going to Unicode is a lossless operation, right? Because again, it's Unicode, it's universal code, right? And so the idea here is that we always round trip. And you either call encode and decode explicitly or you use types like TextView. And we also have some additional types which don't do things like normalization, but only do the encode, decode, or transcode step. And so the way we do this is we have these encode, decode, transcode views. You basically plug in your range, like a string view. You plug in the encoding, like the narrow execution. Then you say, listen, I'm going to UTF-32, right? And then it just converts, right? And you can use this in a range 4. It's very lazy. It's very simple, right? You can go from any encoding to any encoding as long as their code point types match, right? So this makes it scalable, right? You don't have to like hand write like I'm going from Shift.js Japanese encoding to EBCDIC IBM's encoding, right? You don't have to do that, right? It takes care of the whole round trip for you, right? So your only responsibility is to write one good encoding object, right? That handles the encode and the decode from your code unit and code point types. And then everything else just scales beyond that, right? It's slow, but it scales. And so, this is kind of like a bit of a snapshot of the code that I have already written. So basically, you take the decode result, you call the encoding from, you decode, you check if something went wrong, and you get out of there if you have. Otherwise, you use the intermediate storage to encode to the next thing, and then if an error happens, you leave. Otherwise, you're fine. And it's a very kind of slow process. But obviously, we need to be faster than that, right? I mean, if we always round trip and we do it one at a time, we'll have the same problems as I mentioned before with the C functions. So we want something a little bit faster, right? Like maybe we can't write a whole SIMD optimized thing, but maybe we can transcode between one encoding and another very, very quickly, right? And so this kind of chops out one of the steps in the diagram. And so now you're kind of going from an encoded single input, you're directly transcoding, then you have your single output, right? And so the way you do this is you write this interesting function called TextTranscode1. And this is an ADL function that you can write literally anywhere. And it's a little bit faster, but it's not the fastest. And the idea is that the standard will always look for your version of TextTranscode1 to do this like one-to-one, this one-by-one transcoding. And by doing that, you're allowed to hook the implementation with this very simple, with this function to get the job done. Now, it doesn't necessarily look all that pretty. There's a lot of information coming in here, right? So you need to have the input, the output, the input encoding, the output encoding, output state, decoder, encoder. Yeah, it's a lot. The good news is, if I'm going from UTF-8 to UTF-32, I don't really have to do that much, right? I just have to decode, right? Because the output of decode is already a UTF-32 Unicode character, right? So I don't have to like call decode and then encode again. I just call decode, right? And I'm done, right? And so this is something that the standard will do for you for free, but this is an example of like, I already know, right, that I'm like gonna decode something and it's already gonna be in the right state, right? Like I don't have to do any extra work here, so just decode it, right? Just do that nice and naturally. And so again, the whole idea is that you can write things for like UTF-16 to UTF-8, or maybe one of the Chinese GB encodings to the larger version, the larger UTF version, GB 18030, right? Because GB 18030 is actually like a superset of a lot of the GBK and legacy Chinese encodings. So you can actually sometimes just like directly memcopy. And so in this case, it's still the same interface, right? So you still have this lazy view thing, right? And you're still writing the same code. It just happens to be calling your transcode 1 every time to do a little bit faster, right? And so this is a little bit faster. And you would think that this is not that great, but Zach Lane with Boost.txt has an iterator-based approach that's very similar to this. And he wrote direct transcode from UTF-8 to UTF-16 and whatever. And when we stacked up his implementation in a bunch of benchmarks, his implementation was actually pretty fast. Not the fastest. He didn't compete. He was faster than almost everybody else, but he didn't beat the SIMD hand optimized function, which is something we're going to talk about in a little bit, actually, or right now. So obviously, we need a little bit more. We need a fastest path. We need something that can go blazingly fast, like take all the input, dump it into all the output, right? This is like what your wide-card or multi-byte to wide-card on Windows looks like. This is what the encoding RS that Henrysaponin wrote from Firefox. These are the things that we need to enable great performance, right? So in order to do that, we need to have another hook for that, right? So the first thing that we do, right, is we enable the standard itself to have a way of fast transcoding. So we basically make these new functions, right, called encode, decode, and transcode. And basically what you can do is you can take an input, give it an output encoding, right, and it just transcodes everything, right? The whole thing at once, right? And this is from the example that you saw, in the beginning, right? And so you can take text. This is a little u qualified string literal, which makes it a car16 to or UTF-16 literal, and transcodes it to UTF-8 all at once, right? And the whole point about this is that we need to also enable not only the standard to transcode everything at once, but the users to write a function on top of that has their things called, right? Because the whole point is that the standard can't make every single person happy, right? It needs to be everything for everyone, but, I can't expect Billy O'Neill to spend all his time in the world making sure epsidec to, UTF-8 is very fast, because epsidec is a legacy encoding that basically only exists in the ZOS ecosystem. And while they might get some text in the wild that represents that, and they might have an encoding object for that, they can't spend all their time in the world like SIMD optimizing it or whatever else, right? But IBM is going to care about optimizing epsidec to UTF-8 because, well, their entire ecosystem is based off epsidec, right? So we need to have a way that the user can customize. The person outside the standard can customize all this stuff, right? And so the way you do this is with the text, ND, or transcode functions, right? And so in this case, we have an example of text transcode. You have an input, output. You have the encoding types. You have empty structs. Again, they're empty structs, so we don't care about them. And then we have the decode handler, right? And we're using this weird thing called UTF-utils SC convert, right, which is a SIMD optimized conversion function. And then we check if we hit an error, and if not, we call the decode handler with the necessary parameters, and that's basically how text transcode works, right? And you might think, well, hold on, you're cheating here, right? This UTF-utils SSE convert, like you're gonna have to show some code about this, right? Like, yeah, come on, you can't just cheat and tell everybody it's gonna be fast. But I don't have to, because there's already a very lovely, handsome man named Bob Steagle who did this already. The UTF-utils, the SC convert, he wrote this function. He finished it. He benchmarked it, right? And he presented about it at CppCon a year ago, right? And so he talked about the DFA that he wrote and everything else, and he provided the performance benchmark where he benchmarked not only Zach's library, but his library, right? And he showed that he had a fast SMID optimized implementation, right? And so the whole point is that Bob Steagle, right, working for Company X, can crack open this extension point, put in his UTF-8 utils that they've already hyper-optimized for their architecture, it was a Westmere, and use it, right? So now, it's not on STL, it's not on Jonathan Wakely, it's not on all those people to write fast implementations, right? If you really care and the standard's too slow for you, crack it open and do it yourself, right? Because likely, right, Firefox, Chrome, Bloomberg, IBM, they already all have these implementations, right? So just let them use what they already have, right? They get the nice, they get the nice syntax with the, they get this nice syntax and everything, right? And so they can use this everywhere, but they can still have their implementation, their internals on the inside, right? And that's very important, right? Because what this allows people is to slowly port their code over, slowly take over, and you can have this kind of thing slowly incrementally take over a code base, right? Which is, the whole point, right? We want people to use better things, right? I was going backwards, sorry. So I guess the next thing I should really talk about is accelerating development, right? one of the things that Tom Honerman said when I presented this idea to him and everything, he said, this is foundational work that is needed for C++23 to enable non-experts to write hello world. I mean, not the typical ASCII world, but, Earth America's, emoji world. And so the idea here is that I wrote a paper. It's called P1629. It has a lot of this information, a little bit less because I paused it for this talk. But this paper, right, is a library. It's a purely library thing, right? There's a lot of work I have to do, right, to go to glibc and talk to the musil people and be like, hey, I need to implement 20 extra functions. That's okay, yeah, in their libraries. But this needs an implementation, right? I can't convince implementers of this fully, right? I can give a CppCon talk, I can do X, Y, and Z, but in order to convince implementers fully that this is tractable and workable, I need to be able to produce an implementation of this. And in order to do this, right, I have to, get some sponsorship, right? So the idea is that I want to have an extended implementation by 2020, right? I can do this in my spare time, right? I built, my other library, Sol2, Outpointer, whatever, in my spare time. But this is a very serious undertaking that will take an extraordinary amount of time. And so in this case, right, if we want to see this in C++, if we want to see this supported, if we want to get somewhere quickly, right, I need to spend a lot more time on this than I normally have. And so in this case, right, I'm going to be starting to reach out to individuals and companies, right, to see if they can support having this in C++20, right? Obviously if a certain company gives me, enough funding, I can make it special for them, et cetera, et cetera. But the whole idea is to have something that's early in the C++23 cycle so that we can get the encoding, decoding, normalization parts done and finally start actually talking about the cool parts, right? The bidirectional algorithms that allow us to have Hebrew and Arabic, right, actually in our programs, right, in a sensible, reasonable way, right? Without people having to, be held hostage by ICU. So this is the work I'm trying to do, and so I'm going to be working on getting sponsorships, working on trying to improve the world, working on trying to make the digitally underserved of the world finally have a place in the lowest level language that sits below most of everything else. So if we can do this, right, then we can really accelerate making it easy for people who are just I'm a U.S. person, right, but I don't know more than English, right, but we still want them to be able to have an easy time supporting other people in the world, right? And that's been pretty much the crux of the problem, right? We have systems that make it easy to use ASCII all the time, but we don't have systems that make it easy to use UTF-8 all the time, or to transcode from this, or to handle this script, or to have bidirectional text. And so this is what I'm going to be working on. Thank you. So we do have a little bit of time for questions. So if anyone has any questions or things they want to point out, I'm more than happy to answer. Yeah.
Hello. First of all, very good work, and thank you for already taking this on. One thing that is interesting about a conversion process is that there is one piece of information that is actually being lost in the process. And it's as far as the length of the string is concerned. So when you have some characters that are reducing in length during the transcoding, there can be tables that can be built during the process to keep the displacement information, which can be very useful for certain use cases.
Yeah. So that's something that we're trying to work on with the encoding object, because so I showed the text view and the encoding view and decode thing, right? So a lot of that information is actually supposed to be kept on the iterators to make it easy to do operations. Right now we only have read-only iterators, so that we don't support trying to insert into insert through a view into a sequence, a container, right? But the std text, the basic text types support insertion at random places and et cetera, yeah.
What I mean is that let's assume you've got a piece of text in
Yes.
UTF-8 and you're converting to UTF-16.
Yes.
Well, during that process, at the end, you've got two different strings. But if you had an interval of text in the original string, you can't necessarily map it to the new string without having information on where did the characters get shortened and where
Yeah. So okay. So you're wondering how we preserve size information. So for preserving size information, you'd want to use the lazy interface, because when we give you back the iterators, you can call .base on those, and you get the underlying iterators, right? And that gives you the placement in the original container, right? So in that way, if depending on how many views you stack on, right? So if you have a normalizing view, if you have if you have a grapheme view on top of a normalizing view on top of a decode view, right? You have to call .base a couple times to get down to the base iterator, but you can still retrieve that information, and it is still preserved in that way. Yeah.
Thank you.
Yes. Any other questions? All right. Well, yeah, I'll be here for the rest of the conference, and thank you for listening. Thank you for.